Hi, so welcome to another session. So I hope you guys have gone through the videos and have understood about UART. So today we will be looking into I2C communication, how to do the configuration and the registers, and how we can use this I2C to communicate our data between two controllers. Okay, so let's go and understand the configuration. Okay, for I2C communication, I will be using two STM32 boards, and one I will be making to work as a master and another will be working as a slave. And this is the logic analyzer that I will be using to capture the data sent between these two controllers, bit from master to the slave, and how slave responds to the data. And this I will be capturing in the laptop or PC, and this is how the waveform will look. So one is the clock signal and another is the data. So you can see that the data is communicated, and here we can read the ASCII value what the slave is transmitting. So here you can see that there is a read request from the master. For that there is an acknowledge, and there is a transfer of data happening over this I2C communication. Okay, so let's move into the code and understand how we can configure the two STM board, one as master and another as slave, and can have an I2C communication in between them. So this configuration and reading of I2C data will be similar if we use an normal controller and an I2C slave device. So maybe some IC, slave IC, or maybe some gyroscope which mainly works on I2C. Okay, so these are the two STM controllers that I am using. I am using this breadboard to make the communication loop, and this is the logic analyzer that I will be using to capture the frames. So let's jump into the coding part. Okay, we are in STM Cube IDE. So let's configure one of our Nucleo board as a I2C slave. So for that, let's create a project. Okay, now you can see that some of the pins got configured and the project has been created. So let's first configure our crystal oscillator and timers. So we go to RCC. Okay, so this is fine. Okay, then we go to clock configuration. We select the actual external crystal oscillator, then phase lock loop, and then make it 64 kilohertz megahertz. Okay, the clock configuration is done. So let's go to the pinout and go to the I2C configuration. So in I2C configuration, I will be using this PB9 and PB8. So this will be I2C1 SDA, and it will be I2C1 SCL. So why I am using these two specific pin, because these two pins which are available on this board connectors. So I will be using that. So let's configure I2C mode. So here I will be using standard mode for communication. So let it be in the standard mode. So since this is a slave device, so we need to configure a 7-bit address for the slave device. So give it as an address as 0x12. So we give hex 12 as the primary slave address for this device. So that's it for our configuration. So once more time I am selecting standard mode, which is working at 100 kilohertz of frequency. You can see that 100 kilohertz frequency, and then we are giving a primary slave address of 0x12, that is in hex 12. So this slave also support dual addressing. So one slave can communicate with two masters with two different addresses, and the primary address length is 7-bit, so it can be of 10-bit, but for this we will be using the 7-bit addressing. Okay, now after this, just save the project pressing Ctrl S and ask it to generate the required code. Okay, the code has been generated. Let's check. So this is I2C device, timing has been set, own address is 36. So this is the slave address, 7-bit, and okay. So one thing we missed, that we need to put the slave in interrupt mode, because slave doesn't know when the, yeah, when the master will communicate to it. So it should be working in an interrupt mode, that whenever the master communicates, it should respond. So now enable the interrupt mode and again generate the code. Okay, so now I will be adding two files for with which I can write a custom code to communicate with the device. So let's add two files here. New source file. So I can name it as I2C slave dot c file, and similarly I can add one .h file. So this is the .h file I have added. So now in I2C slave I can add the functions. So let's first add the includes, add the main file, then add string.h. So why I am adding string.h? Because this library function help us to use some of the functionality like malloc, copy, or like mem copy. So that functions are available in string.h. So these I have included here. One more hash include we need to include, that is the I2C slave.h. So that's it for it. So now first thing is that after we start, we need to look for the interrupt coming from the address search. That is when the master will send the request, then it should send with the slave address, so it should look for the slave address. So for that we need to make the slave always be ready in looking for the slave address. So let's look into the APIs available. So this is the API HAL I2C enable listen IT. So it should be in listening mode. So let's copy this and put it into our main function. If I'll enable listen IT and we use I2C1 equals to R underscore. Okay. So if not okay, then we call the error handler. So error handler should be called. Okay. I2C1. Okay. So that's it for here. So in the main file, we are making it enable in the listening mode. Okay. And now let's go to the slave IC. Just copy the handler. Go to the slave.c file. Paste the handler. Make it as external. Okay, so now once the slave is started looking for it, it should receive an callback function whenever there is an address match found. Okay, so let's go here. So to find the callback, so here you can see, yes, I2C address callback. So let's go to this function. Okay, this is a weak function. Let's go and define the function. So in this, we will be getting the callback. So we need to check the direction. So there can be a read request or a write request. For first part, we will be looking into only reading or writing the data into the slave. So let's check the direction first. So transfer direction equals to I to see direction. Okay. So transmit means the master wants to write data. So whenever the master wants to write data after the address match is successful, then it should come here. So when it wants to transmit data, so this if part will be executed, and in else we will be handling the write reading of the data. Okay, so here we can say master wants to write data, and here we can say master wants to read data. Okay, now we need two buffers where we can store the data and from where we can send the data. So let's create a size as define size. So let's create a buffer size of 30 uint 8 underscore t rx data of size. Okay, so here our data will be stored, and similarly uint copy it. Similarly tx data, and then we need a count of this data, tx count and rx count. Okay, so now for the transmission of data we can give some data here. Let me say that when it wants to transmit, okay, what I can write is I can send some character tx data, and here I will say this is new slave. Okay, so this one I will be transmitting whenever there is a read request. So when the master wants to write the data, the first, so one thing we should know that how much data the master wants to write. So we can say that the how the data will be constructed, we can say that the first part of the data will consist of, if the data is like this, the first part of data will contain the length of the data. Okay, then it should contain the actual data 1, data 2, comma data 3, and then dot 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 data n. So first we should tell the slave how many data it is going to receive. Okay, otherwise it will create a problem, that is acknowledgement failure. Okay, so that I will tell you in the upcoming video what acknowledgement failure means. So let's first say that the first bit should be sending the total number of data that the slave is going to receive. Okay, so first we need to check if this is the first time the data is being received. So for that, let's create another variable uint 8 underscore t first data. So first data I am making it 0. So if first data equals to 0, then we will be saving it into the rx, the first data we will be saving. So let's go and check the apis. So we have the slave receive, yeah, we have the slave receive it. So let's go here, hal slave receive it. In hal slave receive it, we have to pass this hal I2C handler. Okay, now we need to know the, sorry, this is the master. We need to have the slave part, slave receive it. So in slave receive it, let's see what all options we have to fill. So first the handler, then the data where we want to store. So we have to store it in the rx data. So rx data. Okay, then the size of data we want to receive. So let's say that we will be receiving the first data. So we receive, just understand this, in the I2C communication the data is received one by one. Okay, so we are saying that we will be receiving only one data, so that we receive the first the length. Okay, here we are giving size 30, so the zeroth data will be of length. So first we are focused on receiving the length. So we receive one, and in this xref option. This is very important thing to understand. So what is an xref option? Let's search the xref option. Okay, so these are the xref options available. So this is nothing but this tells the I2C handler that what type of data it is expecting, like when it should generate an non acknowledgement, that is enact, that it doesn't want to receive any more data or it doesn't want to send any more data. So for that, this xref option is used. So we are saying that we will be receiving only the first frame. So I can say that I2C first frame, this is the first frame here we are receiving. So here I can paste the xref, this one. So we receive the first frame here, and then in the first frame we are receiving the length of the data. So now we need to increment the rx count, as we have received one data rx plus plus, or maybe I can just say the first data to be received is rx plus this one. So rx count is 0, so we receive the rx data. Okay, so every time we enter here, we will make rx equals to 0, and we store the data into the first. So as of now, let's make the master wants to read as an error, so I can call the error handler. Okay, so the error handler is done. Now after there is a slave has received the first data, it will generate a callback function. So let's go here and check what all callbacks available now. So we have this slave rx complete callback. So we will update this slave rx complete callback. So come here, let's define the slave rx complete callback. So in the rx complete callback, we want to receive the other frames, like the other data that is mentioned into the length. That, let's say they say that we want to send 4 data, so we will receive the rest of the 4 data in the I2C callback complete callback. So here we will check if first data equals to 0 is there or not. If first data equals to 0 is there, then we make first data equals to 1. Then we copy the entire thing. Okay, and here we will say rx plus plus. Okay, and then we update it with the rx data first index, as the first index will contain the length. So we update with rx data first index, and this will be the last frame. So when we say last frame, then it will try to capture the data till the number of data present here, and it will store it into the last frame. So here we will say that the address is rx plus 1. So the it will start receiving the data from the one position, from the first position, and it will store the remaining data here. So when this is finished, then it will come to the else once more, and in the else we will just make it again back to assign it 0, and we'll make rx count also 0 here. So maybe this will be the scenario, and we may not require to make it 0 here. Count, let's not make it 0, let's make it aligned with whatever the length of data we are receiving. So rx count will be total number of actual data received will be equal to this one. So as of now, the receiving part is done. So let's define another handler, the error handler also. Let's write the function for I2C error handler. So let's go to I2C R layer. So okay, this is the I2C error handler function. This is a weak function. Let's go and declare the function. So when the error handler is called, for now we don't want to do anything and just want to restart the listening of that I2C slave. So for that, let's go here and just copy this one, I2C HAL enable listening, paste it here. Okay. So that's it for the receiving part. So let's build the code and see for error. Okay, there is no error or warning. Okay, let's flash the code. So when you select the debugger, then here in ST-Link, now since I have connected two controllers, so if I scan it, so you can see there are two debugger link available. So what I can do is I can disconnect the master because I am now flashing the slave. So now if I go to the debugger and go to debugger setting and try to scan it, so you can see that only one debugger will be shown. So in this way you can flash the code into that particular controller which you want to work as a slave. Okay, so the flashing is done. Okay, now let's go and write the code for the master. Okay, now let's create a project for the master. Okay, I will be using the board selector. So I am using F401RE Nucleo board as a master. So give it the name I2C master. Next, and then press finish. Okay, the master has been configured, like the board has been configured with some predefined pins. So I will be using PB9 and PB8 for the I2C. So these are these two pins with the connectors. So let's go for the RCC crystal oscillator. Okay, these are fine. Let's go to the clock configurator. Okay, the clock configuration also looks okay. Nothing to change in clock configuration. Let's go to I2C setting. Select I2C. Now here keep everything standard without any changes. Just select triggers for event and error and press Ctrl S and generate the code. Okay, basically the I2C master doesn't need to do a lot of things. So what we are going to do is we are going to write some data to the slave using this I2C master. So I2C has been configured. So now let's go and add two files to for master communication. So this will be I2C master.h. Copy the same file name and similarly create another file I2C master.c. So here just include the files hash include, and let's go to the main file and copy the handler, the I2C handler in the master.c file as extern. And now let's create two function. Let's say write data void write data. In the write data we will pass the data to be written. Let's say event 8 underscore t star data pointer p data pointer to the data, and event 8 underscore t as length of the data that I want to write. Okay, so here now we will have to save the length in the first byte of the data that we want to transfer. Okay, for that let's create to one data buffer event 8 underscore t tx data of, let's say, let's define the size as define size 30. So maximum of size 30 we will be using. Okay, and then what we need to do is we need to include one more library for using the memcopy function. So let's do a memcopy. So first we will be saving the length in the starting address. So tx data 0 should contain the length. Okay, and then after this we have to do the memcopy. So in memcopy, to which address we want to copy, that we have to give. So that will be tx data starting from the first location, ampersand tx data to p data, and the size is len. So this much will be copied, and then we need to call the I2C function to transmit the data. So that will be hal underscore I2C underscore master. So master transmit. So in this, okay, one more thing we need to declare is the slave address. So let's declare the slave address as define slave address. So slave address was 0 cross 1 2. So now interestingly, the slave address here will be written in 8-bit, but we are only using 7-bit. So we have to shift 1 bit. So here I can say that device address event 16 underscore t device address equals to slave address shifted by 1 bit. Okay. Okay, shifted by 1 bit. Okay, and p data, instead of p data we have to pass the tx, and size should be the len plus 1, since after length we also need to send the tx. Here the tx length is there, and after that the p data. And for timeout, let's give it 1000. Okay, so that's it about writing the data. So let's include this file in the main function for the master. Okay, save it, and then call the write function from the while loop that we want to have a continuous write. So write data. So here we need to pass the data that we want to write. Let's say I will try to write character tx data value should be, this is master 1. Okay, so this I want to write. Okay, now tx value is there, this is master 1. So let's calculate 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. So we want to write 16-bit, so it will be 16. And we could have calculated the size of also, but let's not use that and just pass this one. Yeah, that's it. And let's give it a delay, underscore delay of 1000. Okay, so this is done. So let's build the code for the master. Okay, we have one warning. What is the warning? He said write data. Okay, in the I2C master, let's do a declaration of write data. See now. Okay, it is saying void p data is uint. Okay, so let's do the typecasting. uint 8 underscore t star. Okay, now build it. Okay, zero error, zero warning. So again, when we want to do the debugging, let's remove the slave and just download it to the master. So for that, let's scan the debugger. Okay, so we should have only one debugger available. Okay, so I have. Okay, so the download is complete. Okay, okay, now let's connect the slave and try to check if we receive some data. So let's go to the slave IC and go into the debug mode. Okay, the slave IC has started. A live expression. Yeah, see, we have already received the data that this is master one. So we are actually receiving the data. So if I open the logic analyzer and start the recording, so there are some data being sent. So let's see what data is being sent now. Okay, so let's start the logic analyzer. Okay, so let's see the data being sent here. Okay, see here, this is the data that is being sent. So if I zoom it, you can see that the first thing is the address with a write, then we get an acknowledgement, then we start sending the data from the master end, 1 byte by 1 byte. So every character is 1 byte. In this way, we are writing the entire data to the master. So that is it for this video. I hope you understood how you can make two controller communicate with each other as a master, and you can send the data, write the data from master to slave. In the next video, I will be explaining how you can read a particular data from the slave via the master, okay, over I2C. So that will complete our entire video series for I2C communication. So if you have any doubt, please put into the comments so that I could make that one or in the next video. Okay, thank you.